Welcome. Let your shoulders sink into whatever is holding you right now, and let your breath find its own slow rhythm. There is nothing to do here but listen, and nothing to remember. Tonight we drift toward a pale blue world far out at the edge of the solar system. In 1781, a musician turned astronomer named William Herschel pointed a homemade telescope toward a faint point of light. He had found a new planet, the first one discovered in human memory. At first, Herschel believed he had simply found a comet drifting through the dark. The object had no sharp tail, no blazing trail of ice and dust, yet its strange steadiness puzzled him for months. Astronomers across Europe examined his notes and slowly agreed. This was no comet at all, but a full planet moving in a wide, patient orbit. It took nearly 2 years of careful watching before the truth settled quietly into place. The name Uranus honors Uranos, the ancient personification of the sky in Greek mythology. Every other planet known at the time carried a Roman name, gods of war, love, or thunder. Herschel himself wanted to call his discovery Georgium Sidus, after King George III, but the German astronomer Johann Bode suggested something older, something tied to the heavens themselves. The name eventually took hold across the world, connecting a distant world to the oldest sky god of them all. For thousands of years, people had traced Mercury, Venus, Mars, Jupiter, and Saturn with nothing but their own eyes. Uranus broke that ancient pattern. It was the first planet ever found through a telescope's lens, rather than an unaided glance at the night sky. In a single quiet moment inside a modest English garden, the boundary of the known solar system expanded outward. Uranus sits seventh in line from the Sun, far beyond the rocky worlds and even beyond mighty Jupiter and Saturn. Mercury, Venus, Earth, and Mars come first, warm and close to their star. Then Jupiter and Saturn, vast and banded. Uranus waits quietly beyond them, a cold outpost marking where the solar system begins to feel truly distant. 84 Earth years pass before Uranus completes a single loop around the Sun. A child born on Uranus would live an entire human lifetime and still not see one full year pass. Its orbit is so wide and unhurried that the planet has completed only a handful of full circuits since Herschel first spotted it in the night sky. Time itself feels different out there, stretched thin across a much larger path. A single day on Uranus lasts only about 17 hours, shorter than a full day here on Earth. Despite its enormous size, the planet spins briskly on its axis, cycling through light and dark far faster than its slow, decades-long journey around the Sun would suggest. Two very different rhythms move together inside the same world, one quick, one impossibly slow. Unlike nearly every other planet, Uranus spins on its side, rolling through space like a ball, tossed gently across a table rather than atop spinning upright. Earth, Mars, Jupiter, and Saturn all rotate with their poles pointing roughly up and down. Uranus alone tips almost completely over, carrying its icy rings and moons along with it in that same sideways roll. 98 degrees is roughly how far Uranus leans from upright, an angle so extreme that the planet is often described as lying on its side. Most planets tilt only slightly, swaying a little as they circle their star. Uranus tips past horizontal entirely, meaning its north and south poles sometimes point almost directly at the Sun instead of up toward the stars. Astronomers place Uranus in a special category called the ice giants, distinct from the gas giants Jupiter and Saturn. Beneath its calm blue-green face lies a deep mixture of water, ammonia, and methane ices, mixed with a smaller share of hydrogen and helium than its larger siblings hold. This icy composition gives Uranus its own particular identity among the outer planets: cold, dense, and unlike anything closer to the Sun. Let your breath slow now, without effort. Notice the inhale, warm and unhurried, then the release that follows it. Each breath carries you a little further from the day's noise, a little closer to rest. There is nothing to solve here, nothing to hold on to. Let your shoulders loosen, your jaw ease, your thoughts drift like slow clouds crossing a wide, dark sky. Just breathe and let sleep find you on its own time. Uranus ranks as the third largest planet in our solar system, measured simply by its width. Only Jupiter and Saturn stretch wider across their equators. Despite lying so far from the Sun, Uranus commands real physical presence, a broad, pale sphere large enough to hold dozens of Earths within its volume. Its size alone marks it as one of the solar system's true giants, vast and pale in the outer dark. By mass, Uranus falls to fourth place among the planets, trailing behind Jupiter, Saturn, and Neptune. Size and mass tell slightly different stories out here. Uranus is wide, yet not as heavy as its icy sibling Neptune, despite being the larger of the two by diameter. This gap between size and weight hints at real differences in what lies packed within each distant world. 4 Earths placed side by side would roughly span the width of Uranus. Its diameter reaches about 50,000 kilometers, dwarfing our own modest, rocky home. Standing on some imagined surface and looking outward, the horizon would curve away far more gently than on Earth, stretched across a world 4 times as wide. The scale is difficult to hold in the mind, yet restful to consider. 14.5 Earths could balance against Uranus on some impossible cosmic scale. That is roughly how much more massive this ice giant is than our home planet. All that extra weight comes not from rock, but mostly from thick layers of ice and gas pressed together under gravity's steady hand. Mass, here, means something colder and airier than it does on Earth. That pale blue-green glow, drifting through telescope lenses, comes from methane high in Uranus's atmosphere. Sunlight reaches the planet, and methane absorbs the red wavelengths, letting blue and green light scatter back toward any watching eye. The effect is subtle, more a wash of color than a vivid hue. It gives Uranus its calm, oceanic appearance, though no liquid sea exists there at all. Hydrogen and helium make up the bulk of Uranus's atmosphere, much like the gas giants closer to the Sun. These light elements form a thick outer envelope, thinning gradually with height. Beneath that familiar mixture, though, Uranus keeps something rarer, denser ices that set it apart from Jupiter and Saturn. The outer robe is familiar, what lies beneath is not. Beneath its hydrogen-helium robe, Uranus holds substantial amounts of methane, ammonia, and water, frozen under extreme pressure. These 3 compounds, common in comets and icy moons, exist here in far greater quantities than on the gas giants. They give Uranus its density, its color, and much of its strange internal chemistry. Ice, in this distant world, plays a starring role rather than a minor one. Uranus and Neptune stand alone in the solar system as its only ice giants, a category distinct from the gas giants and the smaller rocky worlds. Both share thick, icy mantles, bluish hues, and modest sizes compared to Jupiter and Saturn. Together they mark the quiet outer edge of the planetary family, cold and dim, twins in composition, though not in exact size. 2.9 billion kilometers, on average, separate Uranus from the Sun, a gulf so wide that sunlight itself takes hours to complete the crossing. At that distance, the Sun would appear as little more than a bright, distant point of light, offering warmth too faint to notice. Uranus circles through this cold outer region once every 84 years, tracing an enormous, slow loop through the dark. Sunlight takes about 2.7 hours to reach Uranus, crossing the vast gap between the Sun and this distant world. On Earth, the same light arrives in just over 8 minutes, a reminder of how far outward Uranus truly sits. By the time its rays arrive, they have long left the warmth of the inner solar system behind. That journey unfolds across a stretch of space wider than words can easily hold. For a few moments, let sound become your only companion. Notice whatever hums at the edge of hearing: a fan, the hush of night air, the rhythm of your own breath. Let each sound arrive and fade, asking nothing of you. There is no need to follow it anywhere. Let your shoulders sink into the mattress, and let this hush carry you a little further from thought, a little closer to sleep. Uranus has 13 known rings encircling the planet at varying distances, thin and faint compared to the wide bands people often picture around Saturn. They stretch in a delicate series, each holding its own name and character. Together they form a sparse, understated system, closer to a whisper than a spectacle. Even now, astronomers continue refining their count as fainter structures slowly come into view. 1977 marks the year astronomers first confirmed rings around Uranus, decades after Saturn's had become a familiar sight. The discovery came almost by accident, while researchers watched a distant star fade briefly as the rings passed in front of it. That fleeting dimming, timed carefully from telescopes on Earth, revealed structures too faint to see directly. It was found not by looking straight at the planet, but by watching its shadow cross a distant light. Uranus's rings are far darker than Saturn's, absorbing most of the light that reaches them rather than reflecting it outward. Where Saturn's rings shine with icy brightness, Uranus's appear closer to charcoal or soot in tone. This darkness likely comes from organic compounds mixed into the ring material, aged by long exposure to radiation. Even under direct sunlight, they would look more like shadow than shimmer. 28 moons currently orbit Uranus, a scattered gathering of icy bodies ranging from broad worlds to tiny fragments only kilometers across. Some circle close to the rings, shepherding loose particles into orderly paths. Others drift far out, tracing wide, slow loops around their parent planet. Together they form a small, cold family, each moon adding its own faint note to the system's overall stillness. Unlike most moons in the solar system, Uranuses are named after characters drawn from the plays of Shakespeare and the poetry of Alexander Pope. Miranda, Oberon, Titania, these names carry the cadence of old verse rather than mythology. The tradition began with William Herschel's son, John, who suggested literary names fitting for a planet already tied to the sky rather than the usual gods and heroes. It gave the Uranian system a distinctly literary identity, unlike any other planet's family of moons. Miranda, Ariel, Umbriel, Titania, and Oberon stand as the 5 largest moons circling Uranus, each distinct in size, color, and history. Miranda is the smallest and closest of the 5, while Oberon orbits farthest out. Between them lie varied surfaces, cratered, cracked, streaked with ice, each telling its own long story of formation and change. Together they form the core of Uranus's moon system, the 5 worlds most often pictured when people imagine this distant planet's companions. Titania holds the title of Uranus's largest moon, spanning roughly 1,578 kilometers across. Its surface shows signs of ancient canyons and fault lines, suggesting a history of internal movement long ago. Ice coats much of its terrain, reflecting faint sunlight back into the dark. Named for the Queen of the Fairies in Shakespeare's writing, Titania rules over Uranus's moons in scale, if nothing else. Miranda, smallest of the 5 major moons, holds some of the most varied terrain found anywhere in the solar system. Its surface shifts abruptly between smooth icy plains and jagged, canyon-cut regions, as if patched together from different worlds. Towering cliffs rise unexpectedly from otherwise level ground. No single event fully explains this patchwork appearance, though ancient collisions and internal upheaval both likely played a part. Voyager 2 remains the only spacecraft ever to visit Uranus. Launched by NASA in 1977, it carried instruments built to study worlds no human eye had seen up close. Its long journey outward took nearly a decade before it reached this pale planet. For a brief moment, humanity's only close look at Uranus passed through the sensors of a single wandering probe sent far beyond the orbits of the inner worlds. In January of 1986, Voyager 2 swept past Uranus after traveling 9 years through the solar system. It came within about 81,000 kilometers of the planet's cloud tops, closer than any spacecraft before or since. Cameras and sensors gathered images and readings in the short hours available. That single flyby remains, even now, humanity's only direct encounter with this distant, quiet world. Let your shoulders sink a little further into whatever is holding them. There is nothing left to hold on to, nothing that needs your attention tonight. Feel the mattress or the chair, receive the still weight of you, exactly as you are. Your hands can rest open, fingers loose, unclenched. Let this stillness spread from your fingertips through the rest of your body, drifting further from wakefulness with every breath that passes. Voyager 2's close observation window lasted less than a single day. Within those brief hours, the probe had to gather everything it could: images of the clouds, readings of the magnetic field, glimpses of moons rushing past. There was no second pass, no chance to return for a better look. Scientists spent decades afterward studying that narrow slice of data, still finding new questions inside it. Uranus's magnetic field tilts nearly 59 degrees away from its axis of rotation. On Earth, the magnetic and rotational poles sit close together, nearly aligned. On Uranus, they diverge sharply, tumbling as the planet spins. This mismatch gives the magnetic field an unusual, wobbling character, unlike anything found on the other giant planets. This magnetic field is not even centered on the planet's core. It sits offset, shifted from the middle by a significant fraction of Uranus's radius. Instead of behaving like a simple bar magnet at the planet's heart, the field seems to originate somewhere off-center, somewhere still not fully mapped. The result is a magnetosphere, unlike the tidy, symmetrical fields of Earth or Jupiter. Uranus's extreme tilt gives rise to seasons lasting roughly 21 years each. Because the planet lies almost on its side, sunlight falls in long, uneven stretches across its surface as it orbits. A single Uranian season stretches across 2 decades of human time. A child born at the start of a Uranian summer could reach adulthood before that same season ends. Each pole experiences 21 years of unbroken daylight, followed by 21 years of darkness. During a long summer, the sun never sets over one pole, circling instead through the sky without dipping below the horizon. Then, gradually, that same pole tips away, entering a night that will not end for decades. Nothing on Earth quite compares to a day or a night stretched across so much of a lifetime. That pale blue-green color comes from methane drifting high in Uranus's atmosphere. Methane absorbs red light from the sun and lets blue wavelengths scatter back towards space. The effect is subtle, more like a faint wash of color than a vivid hue. It gives Uranus its calm, cool appearance, distinct even from Neptune's deeper blue. The ring system surrounding Uranus includes both narrow, dense rings and broader, dustier bands drifting farther out. Some rings appear as thin, tightly bound threads of icy debris. Others spread wide and faint, more like scattered dust than solid structure. Together they form a layered system, quite unlike the broad, bright sheets that circle Saturn. Among Uranus's 13 rings, one outshines the rest. Called the Epsilon Ring, it is the widest and brightest band circling the planet. Made of icy chunks mixed with dark dust, it reflects just enough sunlight to stand apart from the blackness around it. Voyager 2's cameras caught its faint gleam during the historic flyby. Even at its brightest, The Epsilon ring remains a whisper of light, far dimmer than anything glowing around Saturn. Uranus holds a curious record among the planets. No world in the solar system has registered a colder atmospheric temperature than Uranus. Its upper atmosphere sinks into a chill deeper than anything measured on Neptune, Saturn, or Jupiter. Planetary science links part of that chill to Uranus's puzzling internal heat, which leaks outward far less than expected. That one detail hints at deeper mysteries still folded inside the planet. -224 degrees Celsius marks Uranus's lowest recorded temperature. That figure ranks among the coldest ever measured in any planetary atmosphere in our solar system. At that depth of cold, ordinary gases behave differently, and clouds form from ices unfamiliar on Earth. Voyager 2's instruments captured this reading while passing through the planet's outer layers. It remains a quiet reminder of how far Uranus drifts from the sun's warmth. For a moment, let your attention rest on sound alone. Not the sound in this room, but something farther off, a hush of air, so faint it barely counts as sound at all. Let that hush be all you need to notice. Your shoulders can loosen without any effort. Your breath can lengthen on its own, unhurried, needing nothing from you right now. Neptune sits farther from the sun, yet Uranus runs colder still. Logic would suggest the more distant planet should hold the deeper chill, but Uranus defies that expectation. Something inside Uranus seems to trap or waste its own heat before it ever reaches space. Neptune, despite the added distance, glows with more internal warmth than its neighbor. The imbalance remains one of the quieter puzzles of the outer solar system. Every giant planet radiates some warmth left over from its formation, but Uranus offers strikingly little. Jupiter and Saturn both glow with heat far beyond what sunlight alone could explain. Uranus, by contrast, barely rises above the trickle of energy it receives from the distant sun. For a planet of its size, that near silence in heat output stands out as unusual. The mismatch has puzzled observers since Voyager 2's instruments first measured it. Uranus's internal heat budget breaks the neat rules that usually describe planetary formation. Standard models predict that a planet of its size should still be shedding warmth from its earliest, hottest days. Uranus instead behaves as though most of that primordial heat has already vanished or become trapped somewhere deep inside. Planetary scientists have adjusted their models again and again to account for the shortfall. The question of where that missing heat went remains unresolved. For decades, Uranus's rotation period resisted easy measurement. Its atmosphere shows so little visible texture that tracking a single cloud feature across the planet proved difficult. Astronomers instead relied on radio emissions and shifting magnetic signals to estimate how quickly the planet spins. Eventually, a rotation period near 17 hours emerged from that careful work. Even now, the exact number carries a small margin of uncertainty. Hubble and Keck telescopes have both caught glimpses of bright storms flaring briefly across Uranus's atmosphere. These storms appear as pale, fast-moving clouds high above the planet's muted haze layers. They rise unexpectedly, brighten for a time, then fade back into the soft blue-green backdrop. Ground-based observatories using adaptive optics have made these fleeting features easier to detect. Each storm offers a rare, brief window into weather patterns still not fully understood. In 2014, astronomers observed an unusually large storm system spreading across Uranus's face. It grew bright enough to be detected by telescopes on Earth, an uncommon event for such a normally subdued planet. The storm's scale suggested deeper atmospheric forces stirring beneath the surface haze. Researchers tracked its brightness over several nights, watching it shift and evolve, it remains one of the most vivid storm events ever recorded on Uranus. Uranus's cloud bands hide behind a haze that stretches high above the planet's visible face. This thin, high-altitude layer scatters and blurs whatever motion stirs beneath it. Where Jupiter and Saturn display bold, distinct stripes, Uranus offers only muted whispers of pattern. Telescopes must strain to detect any variation across that pale blue-green surface. The haze itself becomes a veil, softening the planet's inner weather into near invisibility. Roughly the width of planet Earth, that is the best estimate for the size of Uranus's core. Deep beneath thousands of kilometers of atmosphere and icy mantle, this modest sphere may hold most of the planet's rocky material. Its size seems almost small compared to the vast bulk surrounding it. Pressures bearing down from above make the core's true nature difficult to picture. Models built from gravity measurements offer the closest guess available. Beneath Uranus's outer clouds, matter is thought to flow rather than sit as solid stone. Planetary scientists picture a deep layer of icy fluid, dense and slow-moving, filling most of the planet's middle region. Unlike a rocky terrestrial world, Uranus offers no clear boundary between solid and liquid. Pressure and temperature climb together with depth, blurring any sharp line between states of matter. The result is an interior that resists simple description. The mantle of Uranus is modeled as a slushy blend of water, ammonia, and methane ices. This mixture behaves less like the ice found on Earth's surface, and more like a heavy, flowing syrup under extreme pressure. Researchers studying such conditions describe it as neither fully liquid nor fully solid. Deep within Uranus, this slush likely stretches across a vast portion of the planet's volume. Its exact texture and behavior remain difficult to reproduce in any laboratory. Let a little warmth settle into your shoulders now, spreading down through your arms like sunlight through a thin curtain. Feel it pool in your hands, your chest, the backs of your knees. There is nothing to hold, nothing to solve, nothing waiting for you tonight. Let that warmth carry your thoughts further away, past the edges of today, into wherever rest is found. In models built by planetary physicists, Uranus's mantle might host a strange state of matter called superionic water. Under crushing pressure and intense heat, water molecules could split apart in a peculiar way. Oxygen atoms stay locked in a rigid lattice, while hydrogen atoms move freely through it. This unusual combination has only been recreated briefly in laboratories on Earth. Inside Uranus, it may exist as an entire hidden layer. Superionic water conducts electricity while holding together like a solid crystal. This odd pairing lets it carry electric currents even though its outer structure barely shifts. Physicists first glimpsed this state under laboratory shock compression, using brief pulses of extreme pressure. If such water exists inside Uranus, it could help generate the planet's magnetic field from deep within. The idea reframes solid and liquid as far less separate than they seem on Earth. Deep inside, Uranus's structure appears strikingly different from Neptune's, even though the two planets are close in size and composition. Voyager's brief visit and later modeling suggest their internal layouts diverged at some point long ago. Neptune seems to radiate steady internal heat, while Uranus stays unusually quiet. Something in their early histories, or in the arrangement of their inner layers, may explain the contrast. Two ice giants, so alike from the outside, seem to hide very different worlds within. Models of Uranus's interior show none of the clearly defined layers seen in other giant planets. Jupiter and Saturn are often pictured with distinct zones, a rocky core, a metallic hydrogen layer, an outer envelope of gas. Uranus's structure resists that same tidy division in most simulations. Boundaries between its layers may blur gradually rather than break sharply. Some computer simulations now treat the planet's interior as a single, continuously shifting gradient instead of stacked shells. Something about Uranus's interior may be more thoroughly mixed than once assumed. Earlier models pictured distinct shells of gas, ice, and rock stacked neatly from surface to core. Newer simulations suggest those boundaries could have blended across billions of years, folding materials together rather than keeping them separate. If true, the planet's insides might resemble a slow-churn blend more than a layered cake. This shift in thinking continues to reshape how researchers imagine Uranus's hidden depths. Large-scale convection, the great churning motion that stirs many planetary interiors, may be largely absent inside Uranus. Instead of vast currents rising and falling through its mantle, movement there might be slower and more localized than what drives Jupiter or Saturn. Several computer models built from limited flyby data arrive at this same quiet possibility. If confirmed, it would mark Uranus as an unusual case among the solar system's giant worlds. Its interior may simply move less than its neighbors do. Heat inside Uranus may struggle to rise without strong convective currents to carry it outward. On planets like Jupiter, convection acts like a slow conveyor belt, ferrying warmth from the deep interior toward the visible clouds above. Without that conveyor, Uranus's internal heat could stay trapped far below the surface. This idea offers one possible answer to a puzzle that has lingered since Voyager's flyby: why Uranus glows so faintly with heat of its own. The planet may simply be holding its warmth close. Strange fluid motions deep inside Uranus may help explain why its magnetic field leans so far from its spin axis. Earth's magnetic field stays close to its rotational poles, shaped by orderly currents in its core. Uranus's field tilts nearly sideways instead, hinting at movement that is uneven, patchy, or oddly distributed within its icy mantle. Researchers modeling these currents find that irregular flow patterns could naturally produce such a skewed field. The planet's inner motion, it seems, matches its outer strangeness. As Uranus spins on its near-sideways axis, its magnetic field trails out behind it in a long, twisting corkscrew shape. This unusual geometry comes from the planet's odd combination of rapid rotation and extreme tilt working together in the solar wind. Seen from afar, the shape resembles a giant spiraled ribbon stretching millions of kilometers into space. No other planet in the solar system produces quite this pattern. It is one more way Uranus turns its geometry into something wholly its own. Every few hours, as Uranus completes part of its rotation, its magnetosphere opens briefly to the passing solar wind, then closes again like a door swinging shut. This rhythmic opening allows charged particles to slip inward for a time before the boundary reseals. The cycle repeats steadily, tied to the planet's odd tilt and quick spin. Researchers compare it to a slow, rhythmic breathing of magnetic energy in and out of near space around Uranus. Let warmth settle into your hands and feet, spreading up slowly through your arms and legs. There is nowhere to be right now, nothing to solve, nothing to hold on to. Each breath draws that warmth a little deeper into your chest, easing the space behind your eyes. The mind can rest here, unhurried, while the body grows heavy and still. Let it happen on its own and drift. Unlike Earth's magnetic field, which stays relatively steady across centuries, Uranus's field seems to shift and wobble in ways that resist easy prediction. Measurements from Voyager's brief pass showed a structure so lopsided and irregular that modeling its behavior over time remains difficult. Earth's field drifts gradually, but Uranus's appears to lurch, changing shape and strength without settling into any lasting order. The planet's magnetism may simply behave by different rules than the fields we know closer to home. Auroras have been glimpsed glowing faintly near Uranus's poles, captured in ultraviolet light by orbiting telescopes. They flicker far dimmer than the brilliant auroral rings that wrap around Jupiter, where the light show can outshine entire cities' worth of energy. Uranus's version stays subtle, a pale shimmer rather than a blaze. Its weaker magnetic environment and greater distance from the Sun likely explain the difference. Even faint, these lights confirm that Uranus's magnetic field still interacts actively with the solar wind. Charged particles drifting near Uranus's rings and moons may be steered by its irregular tilted magnetic field in ways still being mapped. Instead of following tidy paths like those seen near Earth or Jupiter, these particles might trace looping, uneven routes shaped by the field's odd geometry. Early modeling hints that this could alter surface chemistry on nearby moons or subtly darken ring particles over time. The connections remain tentative, drawn mostly from simulation rather than direct observation. Uranus's magnetism, it seems, touches nearly everything nearby. On Miranda, towering cliffs rise from a surface unlike almost any other moon in the solar system. Some walls plunge for kilometers in nearly vertical drops, hinting at a history of internal upheaval rather than simple, quiet aging. Ridges, grooves, and smooth plains sit oddly close together, as if patches of terrain were stitched from different eras. Whatever forces shaped this small moon left it looking pieced together rather than uniform. Miranda's landscape still puzzles those who study Uranus's family of moons. Verona Rupes, a cliff on Miranda, ranks among the tallest known escarpments in the solar system. Its rim drops nearly 20 kilometers, a fall many times deeper than anything carved into Earth's canyons. Sunlight would take long minutes just to cross its shadowed face. Something once fractured this small moon's crust with tremendous force, leaving behind a wall that has stood undisturbed for eons. Its height alone hints at the violent shaping this small world once endured. Ariel gleams as the brightest, most reflective of Uranus's 5 major moons. Its icy surface bounces back sunlight with a clarity none of its siblings can match, giving it a mild, luminous quality in telescope images. Fresh ice deposits and fewer ancient scars may explain this brightness, suggesting a surface renewed more recently than most. Ariel's sheen stands out even in the dim light so far from the Sun. Among Uranus's moons, it shines like a small pale lantern. Umbriel, by contrast, is the darkest of Uranus's 5 major moons. Its surface absorbs sunlight rather than reflecting it, giving the moon a charcoal hue that Voyager's cameras struggled to resolve in detail. Ancient carbon-rich material coating its crust may account for this deep-shadowed look. Few bright features break its surface, aside from a puzzling pale ring near one crater. Umbriel drifts through Uranus's system like a muted companion to its brighter neighbors. Oberon carries some of the oldest scars in Uranus's moon system, its crust pocked with ancient impact craters. Dark patches near some crater floors may be remnants of cryovolcanic flows, icy material once erupted rather than melted rock. If confirmed, these flows would mark Oberon as geologically active in its distant past. Its heavily cratered face suggests billions of years with little renewal since. Oberon stands as a weathered elder among Uranus's largest moons. Titania's canyons stretch for hundreds of kilometers, tracing a history of internal tectonic motion across the largest of Uranus's moons. Long faults and fractured plains suggest that Titania's icy crust once shifted and pulled apart, perhaps as an internal ocean froze and expanded beneath it. These rift valleys resemble features carved by similar forces on Earth, though built from ice rather than stone. Titania's frozen wounds still trace the outline of forces long since stilled. Something within this moon once moved with real strength. Beneath the icy shells of Uranus's moons, hidden oceans may still exist, sealed away from any starlight for untold ages. Gravitational flexing from Uranus's pull could keep pockets of water liquid despite the deep cold pressing in from outside. If such oceans persist, they would sit trapped between rock below and thick ice above, utterly dark and still. No probe has confirmed this directly. The evidence remains indirect, drawn from surface cracks and subtle shifts in orbit. It remains an open question whether life's simplest ingredients could ever stir in such hidden waters. Let your thoughts loosen now, like knots coming undone in warm water. There is nowhere you need to be, and nothing left to solve tonight. Feel your eyelids grow heavier with each breath, sinking further into the dark behind them. The edges of the room blur into shadow, dim and formless. You can let go now, drifting toward sleep as easily as a leaf settling onto still water. Frozen flows may once have oozed across Ariel's surface, evidence of cryovolcanic activity deep in its ancient past. Smooth plains cutting across older cratered terrain suggest that icy material rose from within and spread outward, resurfacing large sections of the moon. Rather than molten rock, these eruptions likely carried slushy mixes of water and ammonia, freezing solid soon after they emerged. Such activity would have required real internal heat, something small icy moons aren't expected to hold for long. Ariel's smoothed landscape still carries the memory of warmth it should not have kept. Uranus's family of moons may trace its origin to debris left circling the planet after some ancient collision. Material flung outward by that impact could have gradually gathered itself into the round, icy bodies we see today. This would explain why the major moons share similar compositions, as if built from the same shattered material rather than captured separately over time. The idea remains a working hypothesis, pieced together from orbital patterns and surface chemistry. Uranus's moons may be the settled remains of a distant, ancient upheaval. An object roughly the size of Earth may have struck Uranus long ago, tipping the planet onto its side. Such a collision, immense beyond ordinary imagining, could explain the planet's extreme axial tilt better than any other proposed cause. The impact would have redirected Uranus's rotation entirely, setting it on the strange sideways spin it keeps today. Traces of this ancient event may still linger in the planet's uneven heat and its oddly shaped magnetic field. If true, one tremendous moment billions of years ago went on to define Uranus's entire character. This ancient impact may also help explain Uranus's puzzling internal heat flow. The same violent collision that tipped the planet onto its side could have churned its interior, mixing layers that might otherwise have settled into orderly bands. Such turbulence, stirred billions of years ago, may still be releasing trapped energy today. If true, the scars of that ancient event live not only in Uranus's tilt, but in its lingering warmth. Other models propose multiple smaller impacts, rather than one giant collision, tilted Uranus over time. Instead of a single overwhelming strike, a series of ancient collisions could have nudged the planet sideways gradually, each one modest but cumulative in effect. Their combined force might rival one dramatic blow, spread across a longer stretch of time. The truth may lie somewhere between a single moment and years of slow accumulation. Uranus's extreme tilt might also have disrupted the internal processes that generate its magnetic field. Whatever event knocked the planet onto its side may have scrambled the deep currents responsible for shaping a magnetic field, leaving them uneven and off-center. A magnetic field usually forms from smooth, steady motion within a planet's interior. If that motion were interrupted by tremendous upheaval, the resulting field might carry the imprint of that disruption ever since. No one yet knows exactly how Uranus generates its magnetic field internally. Unlike Earth's steady dipole-shaped field, Uranus's magnetism appears lopsided and irregular, hinting at a process unlike anything seen elsewhere in the solar system. Some combination of moving fluids deep within the planet must be responsible, though their exact location and behavior remain unclear. The puzzle stays open, one of the persistent mysteries Uranus keeps to itself. Extreme pressure and temperature deep inside Uranus may cause diamonds to rain toward its core. Under conditions far beyond anything found on Earth's surface, carbon atoms locked within methane could be squeezed into tiny crystalline diamonds. These crystals, once formed, would begin sinking through the planet's dense fluid layers, pulled steadily downward by gravity. The image is startling, yet the physics behind it rests on real laboratory evidence. Laboratory experiments suggest hydrocarbons under high pressure can form diamond rain within ice giants. Researchers have compressed methane and similar carbon-rich compounds to enormous pressures, recreating conditions thought to exist deep inside Uranus and Neptune. In these experiments, carbon atoms separate from hydrogen and arrange themselves into tiny diamond structures within moments. Watching this happen in a controlled setting offers a rare, tangible glimpse into a process otherwise hidden far beneath an ice giant's clouds. Falling diamond rain could release heat as it descends toward Uranus's core. As these dense crystals sink through the planet's fluid layers, friction and compression might convert some of their motion into thermal energy. Over immense stretches of time, this steady downward drift could contribute meaningfully to the planet's internal warmth. A cascade of diamonds falling for eons may be warming the world around it from within. Feel the warmth still held in your blankets, gathered there from your body's own hours of rest. Let it spread outward, easing the tension in your neck, your jaw, your hands. There is nothing urgent waiting for you now, nothing left to hold on to. Let your breathing settle into its own unhurried rhythm, and let that warmth carry you further from waking, deeper into rest. This heat release might help explain part of Uranus's puzzling internal energy readings. If diamonds truly fall and warm the planet as they sink, that trickle of energy could account for some of the unexplained heat measured rising from within. It would not solve the entire mystery on its own, but it offers a plausible piece of a larger puzzle. Even something as small as falling crystals might shape a planet's story. Uranus's core may be surrounded by an unusual hot ice layer with unfamiliar physical properties. Despite its icy name, this material would not resemble the frozen ice found on Earth's surface. Crushed under extraordinary pressure and heated far beyond boiling point, it could behave as something between a solid and a fluid, dense and strange. Such an exotic layer, if it exists, would follow physics rarely observed anywhere else. A well-defined solid core may not exist inside Uranus at all. Instead of a hard boundary between core and mantle, the transition might be gradual, blurring into a slow gradient of ice, rock, and fluid. Certain interior models find no clean seam, only a smooth deepening of pressure and density toward the center. If this is true, Uranus's middle would resemble a fading shadow more than a solid stone heart. Millions of times, Earth's atmospheric pressure could bear down within Uranus's hidden depths. At such crushing weight, ordinary materials stop behaving as they do at the surface of any familiar world. Water, methane, and ammonia might be squeezed into forms with no name in everyday chemistry. Descending even a little further, the pressure climbs faster than the mind can easily follow. Several thousand degrees Celsius may blaze inside Uranus's hidden layers, far hotter than any flame at the surface of Earth. This heat exists not from fire, but from the sheer weight of the planet pressing inward on itself. Far below the pale blue clouds, temperatures could rival the surface of a small star. The cold face Uranus shows the universe conceals a furnace within. Uranus's internal glow seems to match, almost exactly, the warmth it receives from the sun. Where other giant planets radiate noticeably more heat than they absorb, Uranus appears strangely balanced, giving back nearly what it takes in. This quiet equilibrium sets it apart from its siblings among the outer planets. A planet that neither hoards nor releases much extra heat feels, in its own way, remarkably composed. This balance sets Uranus apart from every other giant planet studied so far. Jupiter, Saturn, and even Neptune all glow with detectable extra warmth rising from within. Uranus alone seems to run cooler than expected, its internal engine strangely quiet. Among four worlds shaped by similar origins, one behaves like an outlier no model fully anticipated. Planetary science entertains one explanation for this puzzle: a hidden insulating layer trapping heat deep within Uranus. Such a layer might sit between the mantle and the outer atmosphere, slowing the escape of warmth generated below. If true, heat would linger far longer inside the planet than it otherwise could. A barrier unseen and unmeasured might be quietly shaping everything astronomers observe from outside. A stable, layered interior, rather than a churning mixed one, could explain this trapped heat. If Uranus's insides settle into distinct bands by density, warmth generated near the center would struggle to rise through the layers above it. Convection, the usual engine of heat escape on giant planets, might simply stall. A quiet, still interior, paradoxically, could be the very reason heat stays locked inside. Voyager 2's single flyby left far more questions than answers about Uranus's hidden depths. In its brief pass through the system, the spacecraft gathered what remains, decades later, the only close look humanity has taken. Every model of the planet's interior still leans on that narrow window of data. A few hours of observation continue to shape everything astronomers imagine about a world they have never returned to. Let your attention settle now on the hush around you, the faint hum of distance beneath the silence. Somewhere far off, a sound may rise and fade, and you can let it pass without following it. There is nowhere else to be, nothing left to track. Let each sound arrive softly and dissolve, carrying your thoughts with it, further into rest. Modern computer models attempt to rebuild what lies beneath Uranus's clouds, working only from the fragments Voyager left behind. Researchers feed gravity measurements, magnetic readings, and atmospheric data into simulations that test countless possible interiors. Each version offers a different guess at what pressure, heat, and composition might look like far below the surface. Piece by piece, these models sketch a portrait of a planet still mostly imagined. Subtle irregularities ripple through Uranus's measured gravity field, faint enough that ordinary instruments would miss them. Scientists interpret these tiny variations as clues to mass unevenly spread through the planet's depths. A perfectly uniform sphere would pull evenly on any passing spacecraft. Uranus does not. Something within its layers tugs a little differently, hinting at a structure less symmetrical than its calm blue face suggests. These small gravitational anomalies point toward an asymmetric interior, rather than a planet built in neat, even shells. Mass appears to gather more thickly in some regions than others, as if unseen currents once froze mid-motion. Planetary scientists still work to map exactly where that extra weight resides. The picture emerging is less like a layered cake and more like a slow, uneven swirl of hidden material settled long ago. Planetary science still debates whether Uranus's icy layers are chemically separate from its rocky core or whether the two quietly intermingle. Some models draw a clean boundary, ice above, rock below, in tidy division. Others suggest elements bleed across that line, blurring mantle into core. No spacecraft has ever sampled deep enough to settle the question. For now, the boundary remains a matter of careful modeling, not direct proof. Ammonia deep within Uranus may dissolve into the water around it, once pressure and heat grow extreme enough. This blending could transform an ordinary icy mixture into a fluid capable of carrying electrical current. Conductivity matters here. since moving charge deep inside a planet can help generate its magnetic field. A simple chemical marriage, water and ammonia merging under pressure, might quietly power something as vast as Uranus's magnetism. One line of theory imagines a hidden layer of diamond-laden liquid carbon settled far beneath Uranus's icy mantle. Under crushing pressure, carbon atoms might arrange themselves into countless tiny diamonds, suspended within a slow-moving liquid. This glittering layer, if it exists, would sit far beyond any light, in darkness dense enough to bend the meaning of solid and liquid. It remains an idea sketched from physics, not yet confirmed by direct evidence. Other researchers suggest Uranus's deepest layers may hold ice phases that never form under Earth's mild surface pressures. These ices, exotic by earthly standards, could behave more like metal than frost, conducting heat and current in strange combinations. Laboratory recreations hint at dozens of possible ice structures, each shaped by different pressure and temperature. Deep inside Uranus, ordinary water may take on forms with no everyday name. Laboratory shock compression experiments attempt to recreate, for brief instants, the pressures buried deep within Uranus. Powerful lasers or gas guns slam tiny samples together, compressing them faster than the eye can follow. In that fraction of a second, materials briefly reach states thought to exist hundreds of kilometers beneath Uranus's clouds. These small, controlled bursts on Earth offer researchers their closest glimpse yet of a world they may never visit. High-pressure ice, what physicists call Ice 7, may exist deep inside Uranus, holding a rigid crystal form despite tremendous heat. Under ordinary conditions, that much warmth would melt ice instantly. Crushing pressure changes the rules, locking water molecules into place even as temperatures climb far past boiling. This is ice that would feel nothing like the ice on Earth, dense, hot, and strange, yet still, in its own way, frozen. A number of theoretical models propose a hidden ocean resting between Uranus's icy mantle and its rocky core. This ocean would be nothing like Earth's, not water alone, but a dense fluid mix of melted ices under enormous pressure. It might move, however faintly, in slow currents driven by heat rising from below. If real, this buried sea would mark another layer in a planet built from unfamiliar chemistry and hidden, unhurried motion. Let a sense of warmth settle over you now, spreading from your chest outward to your fingertips and toes. Imagine it moving like a slow tide through your limbs, loosening whatever the day left tightened. There's no need to hold on to anything. Let your breathing find its own unhurried rhythm, each exhale carrying a little more of you into rest. The dark around you holds nothing but stillness, and stillness is enough. Researchers still debate where exactly Uranus's mantle ends and its core begins. The transition may not be a sharp line at all, but a slow blending of ice, rock, and fluid across thousands of kilometers. Some models draw the boundary sharply, others show it dissolving into gradients. No instrument has yet measured. Without better data, the planet keeps its inner architecture folded away, unresolved. Uranus's low heat flow might indicate a hidden boundary layer, blocking warmth from escaping outward. Such a layer would not be solid, but dense enough to slow heat's rise from within. Warmth would gather beneath it, trapped rather than released into the cold above. If real, this hidden layer could help explain why Uranus glows so faintly beside its neighbors. NASA has proposed a dedicated Uranus orbiter and probe mission, aiming for a launch sometime in the 2030s. The plan calls for a spacecraft to circle the planet for years, measuring its gravity, magnetic field, and atmosphere in detail no flyby could ever achieve. An accompanying probe would descend into the clouds themselves, sampling the air on its way down. After decades of waiting, Uranus may finally receive sustained attention. Earlier New Frontiers mission proposals have also considered exploring Uranus, though none were ultimately selected for flight. Teams submitted concepts pairing a flyby with atmospheric entry, hoping to answer long-standing questions about the planet's depths. Each proposal added to a growing case that Uranus deserved closer study. Though unflown, these ideas helped shape the mission now being planned. No orbiter has ever studied Uranus up close, unlike Jupiter and Saturn, both visited by spacecraft that stayed for years. Uranus has only ever known a single, brief encounter. Everything known about its gravity, its magnetism, its clouds beyond that visit comes from telescopes millions of kilometers away. In this sense, Uranus remains the least explored of the solar system's giant worlds. Ground-based adaptive optics have revealed far more atmospheric storms on Uranus since Voyager 2's flyby. Telescopes on Earth's surface, using mirrors that flex to cancel the blur of our own atmosphere, now catch bright clouds and swirling features once thought absent. What had looked like a featureless blue disk turned out to hide considerable weather. Each new observing season adds another storm to the record. The Hubble Space Telescope has tracked seasonal atmospheric changes on Uranus across several decades of patient observation. Its images, taken years apart, show brightness and cloud patterns shifting as the planet slowly moves through its long orbit. Because a single Uranian season lasts about 21 years, only a space telescope with this kind of longevity could ever notice the change. Hubble has become the planet's most faithful observer over time. New images from the James Webb Space Telescope have captured striking new detail in Uranus's rings and moons. Its infrared eyes reveal faint dust bands once invisible from Earth, along with subtle glints from small icy satellites. The rings, thought fully mapped since the 1970s, still hold thin, dusty threads only now coming into view. Each fresh observation adds another layer to an already intricate portrait. A bright polar cap on Uranus, revealed by Webb's careful imaging, remains only partly understood. The cap glows more vividly than the rest of the atmosphere, its edges sharp and strangely defined. It seems tied to the pole currently facing the sun, brightening as that hemisphere tips toward the light. Why it shines so distinctly, though, still escapes a clear explanation. This polar brightening may relate to seasonal shifts in atmospheric photochemistry, sunlight-triggering reactions unseen at other latitudes. As one pole spends decades bathed in continuous daylight, chemical hazes may thicken and reflect more light. The other pole, meanwhile, sits in its own long night, dim and comparatively bare. Over the course of a single Uranian year, this brightness may slowly migrate from one pole to the other. Let your shoulders sink a little further into whatever holds you tonight. Notice the weight of your arms, your legs, settling deeper with each breath you take. There's no need to think about planets or oceans now, no need to remember anything at all. Just let the body rest, heavy and unhurried, while the mind drifts wherever it wants to go. The exact cause of Uranus's polar cap brightness remains unexplained. Webb's images show it clearly, a pale glow gathered at one pole, yet the mechanism behind it stays hidden. It might come from photochemical haze, or from something in the deep atmosphere stirring upward. No single model yet accounts for all its subtle detail. For now, the glow simply exists, watched but not fully understood. Faint traces of hydrogen sulfide drift within Uranus's uppermost clouds, chemists have found. In small enough amounts, this compound carries a sharp, unmistakable smell, familiar from rotten eggs here on Earth. No one has ever stood close enough to notice it, of course. The chemistry alone hints that Uranus, up close, might carry an odor entirely its own, drifting through its frigid outer haze. This trace chemistry sets Uranus apart from its larger neighbors. Jupiter and Saturn's cloud tops glow with ammonia, thick and reflective under sunlight. Uranus, colder and more distant, holds only faint ammonia signatures, its haze shaped instead by other, quieter compounds. The difference points to a colder formation environment, one where different ices condensed and settled into place. Uranus may have formed much closer to the Sun, planetary scientists propose, before slowly migrating outward. Early in the solar system's history, the giant planets were not fixed in their current places. Gravity nudged them, gradually, into new orbits over millions of years. If this idea holds, the pale planet drifting so far from the Sun today once knew a warmer, busier neighborhood. Simulations suggest Uranus and Neptune may have swapped their orbital positions entirely, sometime during the solar system's early chaos. Neptune, in this picture, once orbited closer in, while Uranus drifted farther out before the two traded places. The models fit certain patterns in the outer solar system's small icy bodies. Whether this exchange truly happened remains an open question in planetary dynamics. The NICE model, developed by researchers studying planetary migration, proposes that gravitational tugs from Jupiter and Saturn reshaped the orbits of both ice giants. As the giant planets settled into resonance, their gravity scattered smaller bodies and nudged Uranus into its current wide path. It's an elegant explanation, though still one among several competing accounts of the outer solar system's turbulent youth. Whether Uranus's rings are remnants of a shattered ancient moon remains an open question among researchers. A body torn apart by collision or tidal stress could have scattered debris into the dark, narrow bands seen today. The rings' unusual darkness and their tightly confined shapes lend some support to this idea. No confirmed evidence yet settles the matter either way. Composition of Uranus's rings remains only partially understood, even after decades of study. Unlike Saturn's icy bright bands, Uranus's rings appear dark and carbon-rich, though their exact makeup stays uncertain. Some particles may be coated in organic material, darkened further by long exposure to radiation. Each new observation adds detail, yet the full recipe of these thin, narrow bands still eludes description. Faint dust rings around Uranus have only recently been confirmed, thanks to the sharp infrared vision of the Webb Space Telescope. These delicate bands, thinner and fainter than the main rings, went unnoticed through decades of earlier observation. Webb's imaging revealed their faint glow scattered among the brighter structures. Each thread adds to a ring system far more layered than early flybys ever suggested. Far beyond the moons already named, Uranus may still hide smaller companions in its outer system. Distant orbits there are hard to survey, swallowed by sunlight too faint to reveal much detail. Some candidate objects flicker at the edge of telescope sensitivity, their nature unconfirmed. Each new survey narrows the darkness a little, yet the full census of Uranus's family remains unfinished. The planet's outer reaches may hold more quiet wanderers than anyone has yet counted. For a moment, let the room fall away. Feel the warmth held in the blanket over your shoulders, spreading through your arms, into your fingertips. There is nowhere else you need to be right now. Let your breath settle into whatever rhythm it wants, unhurried, unwatched. Thoughts may still drift by, but you don't have to follow them anywhere. The origin of Uranus's irregular outer moons remains an open question. Unlike the neat, close orbits of its 5 major moons, these small distant bodies tumble along tilted, elongated paths. Astronomers suspect many were captured passers-by, drawn in by Uranus's gravity long ago, rather than born alongside it. Their compositions, where measured, hint at icy wanderers from far beyond the planet's original birthplace. Whatever their history, they now circle in slow, wide loops, distant companions bound to a world they may never have called home. Uranus's small inner moons crowd close together, some barely a breath apart in orbital terms. Gravitational tugs between them may cause slow fragmentation, or in other cases, a drawn-out merging over long stretches of time. Researchers modeling these orbits find some pairs unstable, destined to collide or separate within astronomical timescales. It unfolds far too slowly for any single lifetime to witness. These small worlds still seem to be finding their final places among each other. Several of Uranus's outer moons travel backward, circling opposite to the planet's own spin. Such retrograde paths rarely arise from steady, orderly formation. Instead, they point toward a turbulent past, filled with near misses and gravitational upheaval among the solar system's earliest bodies. A moon moving against the grain likely arrived from elsewhere, caught rather than created. These contrary orbits stand as evidence of a young solar system far less settled than it appears today. Long-term simulations of Uranus's moons reveal a system that may not be as settled as it looks. Small gravitational nudges accumulate over millions of years, shifting orbits in ways too subtle to notice within a human lifetime. Some models find certain moons drifting toward collision courses, while others slowly separate further from their neighbors. The current arrangement, stable for now, may simply be one frame in a slower unfolding story. Uranus's family of moons continues to rearrange itself, one imperceptible step at a time. One of Uranus's smaller, distant moons might, over immense time, migrate inward toward the planet. Should it drift too close, the pull of Uranus's gravity could tear it apart entirely. Debris from such a breakup would likely spread into a new ring, joining the dark bands already circling the planet. It would not happen quickly. Such an ending, if it comes, lies scattered across millions of years still ahead, an event no human record will ever witness directly. How much of Uranus is ice and how much is rock remains debated among planetary scientists. Gravity measurements and internal models offer estimates, but no precise recipe. Water, ammonia, and methane ices likely dominate, mixed unevenly with rocky material sinking toward the center. The exact proportions shift depending on which model researchers favor, and no single answer has yet won full agreement. Uranus keeps its inner composition folded away, offering only clues instead of certainties. Ammonia appears strangely scarce in Uranus's visible atmosphere, far less than expected for an ice giant. This apparent shortage might simply mean the ammonia is hidden, locked away in deep, unseen cloud layers far below what any telescope can reach. Chemical models suggest ammonia could dissolve into water droplets or freeze into invisible layers under certain conditions. What looks like absence from above may instead be concealment, tucked into a cloud deck science has yet to see directly. Beneath Uranus's pale, hazy surface, researchers suspect a hidden layer of ammonia ice clouds may exist, unseen by any spacecraft so far. Such clouds would sit deeper than the methane haze that gives the planet its color, tucked below the reach of current instruments. If real, they would help explain the missing ammonia that puzzles atmospheric models. For now, this deeper layer remains a careful guess, waiting on future missions to confirm or dissolve it entirely. Trace hydrocarbons drift through Uranus's stratosphere, chemical fragments that don't fit neatly into known atmospheric models. These molecules linger far above the visible clouds, formed by processes not yet fully mapped. Their presence hints at chemistry still unfolding in that thin, cold air. Researchers keep sampling starlight passing through the layer, searching for clues that chemistry alone hasn't yet supplied. The trace remains a small, unresolved riddle. A faint haze blankets Uranus's stratosphere, smoothing its cloud tops into pale, even color. This haze may result from photochemical reactions atmospheric chemists have not yet fully identified. Sunlight, thin as it is at that distance, still carries enough energy to break apart simple molecules and rebuild them into something new. The resulting particles scatter light evenly across the disk. No single reaction pathway has been confirmed, and the haze remains real, visible, only partly explained. For now, let the question settle. The way haze settles over Uranus, hanging unhurried in still air. Feel your breath find its own rhythm, rising, falling, asking nothing of you. There is no need to reach for any answer tonight. Let your shoulders loosen, let your jaw release, and let each breath carry you a little further toward sleep. Something beyond the slow decay of radioactive elements may be adding warmth to Uranus from within. A few researchers propose unidentified internal energy sources could be at work, sources not yet named or measured directly. What they might be remains speculative, drawn more from gaps in the math than from firm evidence. The heat itself is real and measured. Its full origin is not. Tidal heating from Uranus's moons has been proposed as one possible source of the planet's internal warmth, though it appears far too small to account for it. The moons are simply too light, and their orbits too steady, to stretch and squeeze the planet the way Io is pulled by Jupiter. The math falls short by a wide margin. Something else, still unnamed, likely carries the heat instead. Heat from the ancient impact that tilted Uranus onto its side may still linger somewhere deep inside the planet. Such a collision would have driven enormous warmth into the interior, warmth that thick ice conducts only very slowly outward. Billions of years later, some suggest that heat still hasn't fully escaped. What began in that ancient encounter might still be fading toward the surface, unhurried, even now. Uranus's core temperature continues to settle, shifting by small degrees even now, long after the planet first formed. Simulations suggest this gradual settling could stretch across timescales longer than the solar system's age so far. Planets rarely reach a final, stable temperature quickly. 4.5 billion years, it turns out, may not be enough time. The interior keeps adjusting, degree by degree, towards some point still ahead. Heat transport inside Uranus may follow physics unlike that of Jupiter, Saturn, or even Neptune. Standard convection, where warm material rises while cooler material sinks, may not apply cleanly inside this tilted world. If that's true, Uranus would be operating under its own internal rules, ones planetary science hasn't finished writing down. A familiar process, perhaps, behaving in an unfamiliar way. Whether Uranus's interior convects the way typical gas giants do remains an open question. In most giant planets, warm fluid rises in orderly currents, carrying heat steadily outward. Uranus's unusually low heat output suggests something may be interrupting that usual flow. Layers of differing composition might resist mixing, holding warmth in place rather than letting it rise freely. The interior may simply move in ways not yet mapped. A slow, layered process called double diffusive convection may govern how heat moves inside Uranus, rather than the simple rising currents seen elsewhere. In this arrangement, distinct compositional layers resist blending, letting heat seep upward gradually, one thin boundary at a time. It is an unhurried, deliberate kind of motion. If real, it would help explain why Uranus's interior seems so reluctant to let its warmth escape. Layered convection like this could trap heat within stable compositional zones deep inside the planet. If distinct layers resist mixing, warmth might settle into place rather than rising freely toward the surface. Heat could linger for ages within a single band, insulated by the layers above and below it. Uranus's faint surface warmth may be the visible trace of an entire architecture holding energy in reserve, layer upon layer, deep within the dark. The same mechanism might also explain the heat mismatch between Uranus and Neptune, two ice giants built from similar ingredients, yet releasing warmth in noticeably different amounts. If Uranus holds heat within layered zones, Neptune's interior may allow that heat to rise more freely. A single physical difference, compounding across billions of years, could account for a puzzle that has followed both planets since their formation. Neptune, despite sitting farther from the Sun, radiates more internal heat than Uranus. Both worlds share a similar size, similar ice-rich makeup, and comparable distances from the warmth of starlight. Yet one glows faintly brighter to infrared eyes, turned toward the outer solar system. The reason for that difference still isn't fully settled, tucked somewhere within the two planets' hidden interiors. Let warmth settle into you now, the way heat settles deep inside a distant planet, unhurried and complete. Feel it pool in your chest, spread through your shoulders, sink into your hands resting at your sides. There is nowhere else to be, nothing left to hold on to. Let the warmth carry your thoughts further from waking, further from tonight, toward rest. This heat discrepancy between two nearly identical ice giants remains an open puzzle in planetary science. Two worlds, shaped by comparable histories, somehow diverged in how much of their birth warmth they still carry. Models can describe the pattern, but not yet explain its cause with certainty. The difference sits quietly in the data, waiting for an answer nobody has found yet. Some propose that Uranus's ancient giant impact permanently altered its internal layering, unlike anything Neptune experienced. A collision violent enough to tip the planet onto its side might also have scrambled or resettled its internal structure. Neptune, spared that particular history, may have kept a more ordinary internal arrangement. One ancient event still shaping how heat moves inside Uranus today. Future gravity and magnetic field mapping missions could help resolve many of Uranus's internal mysteries. Instruments circling the planet for months or years could measure its shape, density, and magnetic behavior far more precisely than a single flyby ever managed. Where Voyager 2 glimpsed a single passing moment, a dedicated mission could watch across entire seasons. Time spent watching, in this case, might finally answer old questions. A dedicated orbiter could measure Uranus's gravitational moments, the subtle tugs and variations that map internal density structure. Tiny irregularities in the pull of gravity reveal where mass concentrates and where it does not. From these measurements, scientists could sketch a clearer picture of what lies beneath the clouds. A planet's interior, traced not by sight, but by the faint signature of its own gravity. Magnetometer data from a future probe could reveal the true source of Uranus's oddly tilted magnetic field. Right now, its origin remains a matter of models and educated guesses built from a single distant flyby decades ago. A spacecraft carrying sensitive instruments could trace the field's shape directly, layer by layer, as it moves through space. The mystery might finally meet its measurement. An atmospheric probe dropped into Uranus could directly sample its deep composition for the first time. Falling through the clouds, it might measure gases, temperatures, and pressures no instrument has ever touched. Every layer it passes would add real data to models built so far on inference alone. A single falling probe, tracing centuries of curiosity into just a few careful hours of descent. Such a probe could help confirm whether diamond rain or supersonic water truly exist within Uranus. Right now, these remain elegant models, built from physics and inference rather than direct observation. A spacecraft carrying the right instruments could search for the chemical and thermal signatures such phenomena would leave behind. Confirmation, if it ever came, would turn imagination into measured fact. Researchers hope future missions will finally explain why Uranus tipped onto its side so completely. The planet's extreme tilt remains one of its oldest unsolved puzzles, dating back to Herschel's earliest observations centuries ago. An ancient collision offers one explanation, but the details remain unproven. New data, gathered directly at the planet, could settle a question that has lingered for centuries. A future mission might determine whether Uranus's moons harbor subsurface oceans capable of supporting life. Beneath their icy shells, Titania, Oberon, and their sister moons may hide water, warmed by tidal flexing or radioactive decay. No lander has touched their surfaces, and no probe has measured their gravity closely enough to know for certain. The possibility alone widens what counts as habitable in this distant part of the solar system. Studying ice giants like Uranus may help scientists understand similarly sized exoplanets scattered across the galaxy. Worlds of comparable size appear again and again among the planets astronomers have found orbiting other stars. Uranus offers a nearby, detailed example of what such distant bodies might be made of and how they might behave. One quiet blue world in this way helps decode countless others too far to touch. For a moment, let there be nothing to figure out. Let your hands unclench, one finger at a time, until they rest open and forgotten. Let your jaw loosen, your shoulders sink further into whatever holds you tonight. There is nowhere you need to be, and nothing left to solve. Just this dark room, this steady breath, this small, drifting stillness. Thousands of exoplanets discovered so far turn out to be similar in size to Uranus, making it a valuable comparison case. Catalogued since the confirmed discoveries of the 1990s, a striking number fall close to Uranus in scale. These distant worlds are far too faint for direct study of their interiors. Uranus, sitting quietly in our own neighborhood, becomes a stand-in astronomers can actually observe and measure. Astronomers use Uranus's atmosphere to help interpret so-called mini-Neptune exoplanets found elsewhere in the galaxy. Many planets orbiting other stars are neither quite gas giants nor quite worlds, and astronomers have come to call them by that name. Uranus shares enough atmospheric chemistry with these distant planets to serve as a working example. Its haze, its hydrogen, its faint methane all offer clues for reading starlight filtered through alien skies. Whether Uranus's interior weirdness is unique or common among ice giants generally remains genuinely uncertain. With only 2 ice giants in our own solar system and neither visited by a dedicated orbiter, comparison stays difficult. Its tilted field, its trapped heat, its uncertain layering could be rare quirks or simply how ice giants ordinarily behave. Without more data, the question simply waits patiently unanswered. Some theorize Uranus's magnetic oddities shift gradually, across centuries rather than years. A field this chaotic might not be fixed at all, but a slow-moving process, shifting the way a very old river changes course over centuries. If so, the magnetosphere studied today could differ from what future observers find in ages to come. Only careful records, kept across many generations, could ever reveal such change. Long-term monitoring will be needed to see if Uranus's magnetic field patterns shift over time. A single flyby, however careful, can only capture one frozen moment in the planet's long life. To notice real change, instruments would need to return again and again, or better yet remain in place, watching season follow season. Future orbiters and long-kept archives may someday reveal whether this field is simply strange or gradually evolving. It remains unknown whether Uranus's storms are linked to deep internal heat leaking upward. Bright clouds appear and fade across its blue-green face, yet no one can say for certain what stirs them. The heat that should power such storms seems barely present at all, and still the storms come. Perhaps warmth from within finds thin cracks toward the surface. Perhaps something else entirely drives this unseen turbulence. Scientists are uncertain whether Uranus's faint internal glow reflects ongoing chemical differentiation. Deep inside, heavier elements may still be sinking, separating from lighter ices around them the way oil parts from water given enough time. If true, this glow could be the planet silently rearranging itself, one imperceptible layer at a time, or it may simply be leftover warmth from a birth 4.6 billion years past. Whether Uranus's strangeness reflects an ongoing process or a frozen ancient state remains unknown. Its tilted magnetic field, its trapped heat, its unfamiliar interior could all be evidence of change still unfolding somewhere deep below. Or they could be echoes of a single ancient event, preserved and unmoving ever since. The planet offers no clear answer, only patterns that could belong to either story. Understanding Uranus's hidden interior could reshape theories of planet formation throughout the galaxy. Ice giants appear common among the many worlds astronomers have found circling other stars, far more common, in fact, than planets like Jupiter or Saturn. If Uranus holds unexpected structures inside, similar surprises may wait inside countless other worlds, drifting around distant suns no telescope has fully explored. Uranus remains one of the least explored yet most mysterious planets in the solar system. Only one spacecraft has ever passed close enough to see it clearly, and that brief visit ended decades ago, leaving far more questions than answers behind. Tonight, its pale disk still turns on its side, far out in the cold dark, unhurried and unwatched. Its mysteries can wait. Yours, for now, can rest too. Let the eyes close, let the breath grow long and easy, and let Uranus keep turning somewhere out, past the edge of your thoughts. Good night.